What we'll be covering a little bit on the Terran1 launch. It was sort of a failure or a partial success, depending on how you spin it. We'll spin it both ways. It does have some implications for 3D printing in general, and Methalox as a fuel, meaning methane and liquid oxygen combination. And part of why they were a success, or partial success, was they got through the most stressful part of a launch. It's called the period of max Q. So I'll talk a little bit about that, just because you tend to hear it, but I'm not sure if everybody knows where it really came from. So the launch of the Terran1, which was a rocket from relativity space, is a brand new one, hadn't been launched before, ever. It did fail. Actually, the first stage worked fine. It was the second stage that failed. So what are the key points about Terran1? Well, one is this 85% 3D printed, which is unusual. Actually, Rocket Lab, they print their engines 3D printing, so it's not exactly unknown. Probably most people making rockets use them to some extent. They just are carrying it much, much further. They're building the whole structure, tanks and everything. The second part of the thing that makes them a little bit unique compared to the old days is that they use methane and liquid oxygen as their propellants. It turns out that actually almost everybody else is now too, but nobody has actually gotten to orbit with this yet, so there's kind of a race going on. One thing about this was back when these companies were founded, which wasn't all that long ago, everybody was enthusiastic about building small launch rockets, and everybody thought that'd be a great market. And there were lots of other companies like Rocket Lab and Astra and some of the others. They all thought it was going to be great. What they've realized is actually there's not much of a market for it. The real market is in launching constellations of bigger satellites. And so this one is probably doomed in the sense that it's an expendable rocket, kind of like the old school rockets. You don't use it once, you can't reuse it. And as a result, it just costs more. So it's probably doomed from an economic standpoint anyway. But the basic problem is that the payload is too small to get real market share. But they kept going with it as long as they did, partially because they had contracts to use it, but also partially because it's really a proof of concept for the rocket they really want to build now, called the Terran1, which is more like a Falcon 9 competitor, kind of medium lift kind of a rocket. And so this is actually a good way for them to demonstrate that they can do 3D printing, they can make it work, and now they just need to scale it up some. And they're pretty far along on doing that. So as I said, the second stage failed, but the first was okay. So they did not make orbit. They will be focusing really on the larger rocket. The larger one, the Terran1, will be actually a serious competitor for the SpaceX if it actually, when it actually works.
I might point out that that little white splash down at the base of the Terran1 picture is actually a human being.
Yeah, I should have said that, yeah. Which makes it kind of comparable to the other medium lift rockets. So anyway, this one will have a reusable first stage and a reusable second stage, and the fairing, which is the nose cone that opens up in most rockets. They actually are apparently going to keep it attached to the second stage. They'll just recover the whole thing all at once. Anyway, it will be a Falcon 9 competition, slightly less payload, but pretty much that's it. So it did partly succeed because it showed that the rocket is strong enough to get past the most stressful part of the launch, which is called the point of max Q. And actually you hear this sometimes in other launches as well. But what is that? What does that mean? Well, again, it's the point where there's the maximum mechanical stress. But why is that? Well, there's this thing called Q, which is dynamic pressure. That's the word for it. There's an equation there. It's just essentially it's kinetic energy. You're used to seeing 1/2 mv squared for kinetic energy. So you take that same mass and you just divide it by the volume, and we get the density, and that's what that is. That's just basically representing kinetic energy. And what is that? Well, you stick your hand out when you're driving in a car, you feel the pressure, and that's what dynamic pressure is. So if you're standing still, you won't feel anything. But if you stick your hand out of a moving car, you feel something. It's beyond the normal atmospheric pressure that you're experiencing. So, in fact, literally, Q is the pressure you would get if wind. Say you're standing still and wind is hitting you. The wind comes to a complete stop. All that energy essentially builds up, and it kind of builds up the pressure, at your outstanding hand if there's a wind coming. If you take the point of view of being on your moving car, you think you're standing still and the wind's coming at you. But either way, essentially, they're coming together, and all that energy is going into pressure. Now, that's not the real situation, but it's a good approximation for what's going on. The units are pressure, like pounds per square inch. So you have the notion of a total pressure, which is basically this dynamic pressure plus whatever the atmospheric pressure is. So we're sitting here in a soup of 14.7 pounds per square inch of normal ambient pressure. If I run really fast, there's a little bit of extra pressure against me. So another way of looking at it, though, is that what is Q? It's the difference between the normal pressure and the pressure you're experiencing, say, at the front of a rocket or something. And that results in stress because you apply that pressure over an area, you get a force. And as a result, there's forces. And the maximum Q is where you're going to get the most stress mechanically. So some examples. At the start of a launch, or for that matter, if you're just in a car standing there, not moving, the Q is 0, no dynamic pressure. And you can see that right from the equation, in fact, there. If rho is atmospheric normal, but v squared is velocity squared. There's no velocity, the value is 0. At the end of a launch, typically you're up in space. Well, there also, you basically have a value of 0 because the density is essentially 0. There is no air up there to speak of, a few molecules here and there, but basically it's close to 0. So you start off with launch at 0, you end up at 0. In between, you've got positive value for density and you've got some velocity. So there's some values in between. There has to be a maximum somewhere. That maximum, that's where max Q is. So during the launch, as you go up, your velocity starts off very, very slowly. It kind of builds up as the speed goes up. But at some point, what ends up dominating is the fact that there's no air left. Density goes down to 0. So that kind of gives you some examples of extreme cases anyway. Remember the movie The Martian, where there was all this damage done by wind and everything? That was actually just totally ludicrous, because if you're getting blown by wind, say 100-mile-an-hour wind on Mars, well, the density is only 1% of the density on Earth. And just from that equation, which is an approximation, but it's, from that equation, basically that's equivalent of a 1-mile-an-hour wind. So that 1 mile an hour was not going to blow you over. It wasn't going to blow over your car. It wasn't going to knock over the greenhouse. None of that kind of stuff. So, but yeah, I know Hollywood can't get everything right. But that's just another example that, this is a real thing. We don't really have to worry about getting blown over when we're walking around on Mars. Just not going to happen. You might object a little bit and say, well, if we said that the Q is if the air goes all the way up to your car or a rocket or whatever it is and stops completely, you say, well, it doesn't really all stop there. Most of it kind of slides around it. That's true. But there are other forces that come in as well, lift and drag. So if you've got the rocket going up, there's friction essentially against the air. Well, it turns out that that force goes up exactly the same way as the dynamic pressure. The equation's there. I mean, people that have raced cars worry about the coefficient of drag on their car. As the speed goes up, the square of the speed, that's how much air resistance you're getting. It still comes down to that value of Q being a part of the equation. So if Q is at a maximum value, multiplying it by a drag coefficient in an area doesn't change where the maximum occurs. So fundamentally, this is actually a pretty useful concept. So anyway, they did that. They showed that they can get past that point. So they take that as a good thing, that it's all smooth sailing from here. By the way, I should mention, this is actually a serious thing. For instance, the space shuttle, when they're getting up to the point of max Q, they actually throttle back on their main liquid engine. You can't do anything about the solid engines. You just light them and they just go. But the liquid engines, they cut them back quite a bit. And as a result, they weren't going so fast while they passed through it, and they got past it. Then they go back to full throttle again.
Throttle up.
Yeah, exactly. You'd hear that kind of thing, go for throttle up after it. So it all comes back to this whole dynamic pressure idea. And people really worried about it because they don't want the rockets to get torn apart by the stresses. Okay, and then the other part of this is the Methalox notion. Methalox is a portmanteau word. Methane plus liquid oxygen, which is abbreviated LOX, L-O-X. And actually, LNG kind of counts in there, liquefied natural gas, because that is really mostly methane. I mean, there's very loose specs on that. It might be 85 to 95% methane, probably close to 95% most of the time. It really gets lumped in there. The next component in that LNG is going to be ethane, and actually its properties are pretty similar to methane anyway. It's just a little bit heavier, a little higher heating value. It's not that different, so you can pretty much treat it. So when people talk about this race to orbit for all the people that want to build Methalox rockets, they include LNG. In fact, if they are going with pure methane, they probably are getting it out of LNG in the first place just by further refining it. Anyway, no one has got to...
If you had a Methalox rocket, you could go down to the corner convenience store and get a bunch of those LNG canisters and use them for fuel.
It's very inefficient, but and probably very expensive, but you could do that. Yes, you could. Okay, so I'm saying here it's kind of a race. Well, really, you go, how come I haven't heard of this? Well, actually, almost everything coming along is Methalox these days. The relativity space ones, the Terran1 we just talked about, and the newer one, Terran, they're there. And I'm going, as I come down this list, I'm going left to right on the rockets here, so you want to get a feel for roughly their heights. This isn't exact, but it's pretty close. So there's that. There's the Neutron, which is coming from Rocket Lab. They too realize they can't make money just selling small rockets. So really, they're making most of their money from selling satellite parts right now, and satellite buses and stuff. But they do have a new rocket called the Neutron coming in, which is more, again, basically all these are Falcon 9 competitors. United Launch Alliance, their new rocket, the Vulcan, That one, it happens to have a Blue Origin engine, which is also a Methalox engine. So it also is going that way. And then, of course, the Starship from SpaceX. And then there's one that most people probably haven't heard of, is a Chinese one, often just called ZQ2. It's already been tested, exactly the same as Terran1, back in December. I think I reported on it at the time. It was the first, but it was just like the Terran. The first stage worked just fine, but the second stage, they actually had an unrelated mechanical failure, and it just didn't work. They actually could be the winner. They're almost ready to launch their second one. So they actually could come in first. It's pretty close. I mean, there's a whole lot of these rockets. They're all happening this year. So it's really more an issue of bragging rights than anything else, but it is pretty close. So why is everybody going to Methalox? And not everybody, but I mean, why is it becoming such a standard? Well, first of all, it's just a heck of a lot cheaper. Because you can derive it from, say, from fracking as a result of the U.S. sources, or LNG if it's shipped over there, it still is a whole lot cheaper compared to the other choices. Hydrogen, I mean, that's just really expensive to generate, in particular to store it and to handle it. It's that part that makes it so expensive. And actually, the same is kind of true for RP1. RP1 is just kerosene, but it's very highly refined. They knock out all the sulfur and a lot of other impurities that get in there. By the time they finish with that, it's just the kind of thing they make in very, very small batches for a very small market. It's just really expensive. So it turns out methane, it's so much cheaper that there's really a compelling reason to use it. It matters now. In the old days, especially when you didn't have reusable rockets and you didn't have so many of them, so you weren't getting the efficiencies of mass production, nobody cared about the cost. Now, actually, the propellant is becoming a higher percentage of the cost of doing a launch, and now it starts to matter a lot more. So that's one of the reasons we're moving to it, compared to either hydrogen or kerosene, which are the two leading liquid fuel contenders besides methane. Now, there are some specific benefits compared to RP1, which is, as I said, our highly refined version of kerosene. That's what the Falcon 9 has. Now, and they're obviously making it work. Can't sneeze at it. But methane is a whole lot cleaner. That means, in particular, even before you burn it, you know, in the fuel lines and everything that go to the engine, it just doesn't leave residue of any sort. So that stays clean. And after burning is even more noticeable. You get a lot of coking, soot generation, that kind of thing. Basically, a lot of partially burned substances, mostly carbon. You get that buildup, and then what that says is you got to clean it out. And it just takes time. And so the less of that you have, the faster you can turn around your rockets. One of the big things about reusability is fast reusability. You want to get the thing back in circulation. You know, if you're flying a plane to Tokyo, it's great that we're reusing the plane instead of throwing it out. But you also don't want it to take 6 months to get ready. The faster you can turn it around, the more efficient it is. So methane is cleaner. You can see that down there at Space Center Houston, actually. They have a Falcon 9 down there. And if you take a look at that thing, it looks pretty grimy. And you think about it, well, that's a booster. It's landing in its own exhaust. And it's just kind of dirty. Yeah. So kerosene is not a clean burning fuel of any sort. Now, also, the other comparison is methane compared to hydrogen. And hydrogen is still used quite a bit, especially in upper stages. It's very efficient as a fuel. And SLS, for instance, is one that uses that. But the thing is, you got to store it. You got a rocket, it's got to have big tanks of fuel. You can store a whole lot more energy, in effect, with methane, or RP1 for that matter. Hydrogen is kind of bad in that regard. The other big thing is, of course, hydrogen is extremely cold. It has to be very, very stored, very, very cold, much more so than either the liquid oxygen or the liquid methane. So you don't need as much weight for the insulation. There's a lot less thermal stress to have to worry about. You have to make sure that the metals don't change temperatures too fast when you're loading it up. I mean, all those things just add all kinds of problems. In fact, you can even have a common bulkhead, meaning in between the liquid oxygen and the methane, you can just use one piece of steel. You know, you don't even have to have separate tanks because they're essentially almost at the same temperature. Hydrogen has other problems like it embrittles metals, which matters a lot. It doesn't matter if you're using it once, but if you want to use it dozens of times, you start to worry about the hydrogen embrittlement, meaning it gets brittle and actually can break. Leakage is always a problem with hydrogen because it's just simple, smaller molecules. And they leak. It's always a problem. But in terms of efficiency, it's actually pretty close to hydrogen. It isn't quite as good, but it's getting close. And then there's the other thing that's kind of in the back of people's minds, especially Elon Musk. He wanted to be sure that he could build rockets that ran on fuel that could be refueled in other planets like Mars. It's not that, in principle, it's not that hard to generate methane as well as the oxygen on Mars. You have carbon dioxide in the atmosphere, and you have oxygen in the water, all that's there. And so with fairly simple, relatively simple chemistry anyway, you can do it. Now, it's still obviously going to be a big engineering challenge to do it at scale, but it's clearly doable. it seems like we better get used to doing things with methane. And that's kind of the view that people have taken, even though it's admittedly more something in the future.
Yeah, because Moxie was successful on Mars, right? The little Moxie,
they were just using it to generate oxygen. That's one of the key reactions, is splitting the carbon. You take the carbon dioxide in the atmosphere is mostly carbon dioxide. You split it in. The main thing was just a proof of concept. But yeah, so they know they can do that part. They wouldn't do it exactly the same way, but at least in general, on a pilot scale, that works. All right, any other discussion or questions?